Join me, if you will, as I recollect my exploration of surface curvature, a topic in differential geometry I had not considered when I was delving into the differential geometry I needed for my PhD thesis in relativistic cosmology. I discovered there are two paths to this topic: the curvature of a surface. You can get at it through Frenet curvature of curves in the surface, or you could look at it as the change in the surface normal as you move in a direction tangent to the surface. So I began with path 1, and that then shed enough light on what they were doing in path 2 for me to make some sense of it. To follow path 1, we need some definitions. Curvature vector. And I put the word Frenet in front to remind us that this is the curvature of a space curve that you would learn about in vector calculus or even a multivariate calculus course. T, unit tangent on a curve. S, arc length, curvature vector, a multiple of the principal normal. In fact, since the principal normal is a unit vector, k is the length of this curvature vector. Normal section. It's a curve. It's a curve in the surface that you obtain by cutting it with what's called the normal plane. Now, if you look at this figure here, some surface that I picked at random, this plane contains the normal to the surface at this point. So it's a normal plane, cuts the surface in this red curve. That red curve is what's called the normal section. The normal curvature is the Frenet curvature of this red curve. This green curve is a tangent to the surface, and the orientation of this green curve, that's this tangent vector, will determine the curvature of this curve because that curve will move. So you look at that normal curvature of those normal sections, and you compute the maximum and the minimum. The maximum and minimum are called the principal curvatures, denoted typically by K1 and K2. The mean curvature is the average of those two curvatures, and the Gauss, sometimes called total Gauss curvature, is the product. So this was the plan that I followed as I began this exploration. I picked a surface, not too wrinkled, but different enough from a helix or the sphere, the standard stuff that you find in textbooks, so that if there was some quirk, it would show up and not be hidden by the symmetry. I picked a point, 115, so I'm dealing with integers. You can see 1, 1, you're going to get the height is 5. You can get a normal pretty easily. You need tangent plane. In the tangent plane, you want a family of tangent vectors because you want to be able to pick different directions of that tangent vector. So that would allow you to get normal planes. If you intersect those normal planes with the surface, you get these normal sections, which are the curves whose curvature you want to compute. Then you get the extreme values of the negative of the curvature, and that minus sign is, we'll see where that comes from later. And you can compare what you compute against calculated values that you can obtain with formulas you'll find on the internet and textbooks and so forth. And then you can get the mean and the Gauss curvature. You can see if what you have computed squares with what these formulas tell you things should be, and you can see if you're on the right track or not. The calculations can get intense, and clearly you want a tool like Maple to make the calculations simpler. So I needed the plots package, and primarily I'll be working in the student multivariate calculus package, but there are commands in the student vector calculus package and student linear algebra package that I wanted to access, and some of these commands occur in both packages, and in order to minimize the conflicts, I load only the one package, and then I alias the long name to the short name. So VC for the vector calculus package and LA for the linear algebra package. And then uppercase Z is the particular surface that I pick to do these explorations. Now we compute some of the surface quantities that we need. Position vector definition of the surface, x, y, z of x and y. Tangent vectors, rx, ry, which are obtained by derivatives of the position vector with respect to its two parameters, x and y. Cross product of the tangent vectors gives you a normal to the surface. Capital U stands for the unit normal. And those vectors are here. Position vector, definition of the surface, tangent vector, normal vector, unit normal. Then sometimes you want this evaluated at the particular point P, so I use an extra subscript P to represent that it's been evaluated at the point where x and y are 1. Tangent vector, normal vector, unit normal vector. Tangent vector, normal vector, unit normal. Then for the family of tangent vectors in the tangent plane, I take a linear combination of the tangent vectors. Now, I picked eventually cos t and sin t as the coefficients of the linear combination. That gives me a one parameter family of tangent vectors. I want to make sure that I'm sweeping the tangent plane with this family of tangent vectors. So I made this little animation where the slider controls the value of t, or the angle t. The black vector is the tangent vector. The red vector is the normal. And I convinced myself that this family sweeps through the tangent plane. And so with that tangent vector, I can obtain enough normal sections that I'm in business. Okay, now what is the normal plane? Okay, it's a plane that will pass through the point 115. It will contain both the tangent and the normal, but this is a family of tangents. Then I solved for z, so I have the planes in the form of z equals, and I use zp to distinguish. This is what that family of normal planes looks like. And you can see here I used the plane command from the student multivariate calculus package. Another animation to make sure that this computation is proceeding the way it should. So what are we looking at here? The moving plane is the normal plane. The green plane is a tangent plane, and these two red vectors, I can show that these two red vectors are the two tangent vectors that we computed. This is the normal vector, and this is the tangent vector that is a member of the family of tangent vectors that I just created. So it looks like I'm in business. It looks like things have progressed the way they should. Then I wanted to see what it would look like if I threw the surface into this picture. So now I have the surface. The green line is the normal direction. I represent it as an axle. The slider controls the tilt of the normal plane, and you can see the red normal sections. These are the curves whose curvature I eventually want to compute. And the animation is bulky because this intersect plot command is the holdup. That's the bottleneck. It's slow, and as you move the slider, you've got to do a whole bunch of computations that are a little bit slow. Now we have enough machinery in place that we can go after normal sections, normal curvature. This is the surface defined implicitly. Normal plane. Now remember where we got the normal plane from, right? We had the expression for the normal plane here implicitly. So intersect them with a solve command. There are two solutions. I call the two resulting curves C1 and C2. And in order to determine which one I should be working with, I evaluated these curves at a particular value of t, and I decided that it was C1 which was passing through the point 115. Let's draw a picture. There's your surface. There is the curve C1. The red dot is the point 115. Over here is the C2. This little red thingy is C2. And then I said, oh, wait a minute. Right there, oh, if I can just hold my hand steady, you see that you switch from C1 passing through this point to C2 passing through this point for a very small range in t. And what is the effect of that? Well, I computed the curvature of C1, and I graphed its negative. And I saw this funny little behavior down here. And I magnified that section, and I saw this behavior. And it's traceable to the switch from C1 to C2 for that small range in t. But I said, let me go ahead and compute the principal curvatures. So I did it numerically, principal curvatures, max and min, of C1. And then I used formulas that gave me explicit values of the curvature, the principal curvatures, and I floated them, and these values matched. So I said, I'm really close. I haven't really made a substantial mistake anyplace. NP is the principal normal. I get it from the vector calculus package. And by putting the word normalize in there, it becomes unit vector. And I want the angle between the principal normal and the surface normal. Okay, principal normal, surface normal. What is the angle? Well, the angle is virtually constant, pi. These two little glitches are probably from this glitch up in here. And that pi says the principal normal and the surface normal are opposed, and that's where that minus sign comes from. So there are formulas for the normal curvature. Here's one of them. C is the curve, n is the surface normal, second derivative, first derivative, norm squared. Well, does it work? Let's try it. So I apply that to C1, second derivative, dotted with the normal, first derivative, norm squared. Z is the parameter along the curve C1, and just refresh your memory where that came from. When we solved for the curve C1, we intersected these two equations, solved them simultaneously, and we solved them for x and y. So therefore, x becomes a function of z, y becomes a function of z, and so the curves C1 and C2 are given as parametrized by z, x of z, y of z, z. So, some simplifications on this expression, and I get this expression for the normal curvature, and here's the graph, and it has the right shape, and it does not have that little glitch down here. So this looks right. Let's obtain K1 and K2, maximum and minimum values of this expression. I use Maple commands for that. Get this number, Maple commands get this number, and I use those two expressions to compute mean curvature and Gauss curvature. Now it turns out that you can pursue these investigations with curves that are not normal sections. Well, how do you get some curves that are not normal sections? So I did this. I took a family of lines in the xy plane. That family is parametrized by P along one of the lines, and T takes you around the family. Lifted those lines up to the surface defined by R, and I get this representation of a family of curves C in the surface that are not normal sections. Draw a picture. So here we have an animation of the curves on the surface. It looks right. They're passing through the black dot, which is 115 on the surface. And I think if you turn this so you're looking down at it from above, let's get it. You can see that you have what appears to be like a family of lines, straight lines. They all pass through that base point, 1, 1. So there appears to be a family of curves in the surface that are not necessarily normal sections. Let's get the curvature. This is the Frenet curvature, and I'm using the vector calculus curvature command. Here I have an expression for the curvature of that family. Principal normal for each curve in that family, and I make it unit vector by saying normalized. The curvature vector is the curvature times the principal normal And I get this as the curvature vector. Then I get the component of the curvature vector on the surface normal. And since these are since n is a unit vector, I just simply take the dot product. And I get this expression. And there are books that claim this is the normal curvature. Well, is it? Let's compare it to the normal curvature that we computed earlier, called Kn. We computed that with this formula. A double prime here, and a single prime here, and a norm. And these two are exactly the same, except minus sign here has been brought inside over here, and it's down here. The effect that minus is down here, see minus 48, 48, 20, minus 20, minus 37, 37. So you can get the principal curvatures from an expression of the normal curvature that you get from curves in the surface that are not necessarily normal sections. Another piece of information connecting these ideas is attributed to this French mathematician. I hesitate to pronounce his name. He is French. The French pronunciation can be found on the internet. Type in the name here. And listen to how it's pronounced in French.
Meusnier. Meusnier. Meusnier.
Okay, I am not going to attempt to pronounce that. My French comes out with a Brooklyn accent, so we'll leave it at that. Okay, so here's the formula. The normal curvature is the Frenet curvature times the cosine of the angle phi, with angle phi is the angle between the principal normal and the surface normal. And it's not hard to see that. The curvature vector is the curvature times the principal normal. The normal curvature is the component of that vector along n. So let's see what happens. Dot k with n, capital N. That should give you kn, the normal curvature, because k is the Frenet curvature, principal normal, dotted with the normal. These are both unit vectors. So all that's left is the cosine of the angle between principal normal and the surface normal. And it actually works. Here's the computation where I verified that it works. Use the angle command in multivariate calculus. Get the angle between the principal normal and the surface normal. It's this. We have already computed the Frenet curvature. Multiply that by the cosine of this angle. You get an expression that looks familiar, and you can verify that it's the right expression by simplifying the difference between the normal curvature that we computed up here and this expression k cos phi. That difference is 0. Now, moving towards a more modern look at surface curvature, we have to consider the notion of the first and second fundamental forms. Here is our position vector defining the surface. We compute these second derivatives, rxx, rxy, ryy. Here's what the vectors turn out to be. 1, 2, 3. First fundamental form has the numbers obtained by rx.rx, rx.ry, ry.ry, and it is a quadratic form. Second fundamental form is also a quadratic form. Numbers are n dot rxx, n dot rxy, n dot ryy. Second fundamental form. Now, in our example, those numbers are going to be these 3, 17, 24, 37, and the matrix of the fundamental form of the quadratic form will be this. I'll call it pi 1. And for the second fundamental form, the numbers are these. And so I have a matrix, -4, -6, 1 over the square root of 53. The interesting result is the normal curvature is the ratio of these two quadratic forms. If you use a unit vector, v hat, then this is 1. And the normal curvature is just the second quadratic form, second fundamental form, using unit vector. Wow. Take some exploration. This is not black magic. It's not hard to see that it's not black magic. Here's this surface, r of x and y. Curve in the surface, parameterized by arc length, r, x of s, y of s. Tangent vector, unit tangent vector, dr ds. Unit tangent vector. How do you get that? Well, the chain rule, dr, dx, dx, ds, dr, dy, dy, ds. If you differentiate the tangent vector with respect to arc length, you will get the curvature vector, which is nothing more than the second derivative of r with respect to s. So let's take a derivative with respect to s of this tangent vector. Product, product, split it. One term, two terms. Okay. The s derivative of this product. The r dx twice. The x ds comes out. The r dx with respect to y. The y ds. And this x sub s is sitting on the outside. Now you hold rx constant and you differentiate x sub s with respect to s, and you get an x differentiated with respect to s twice. And the same pattern holds for this term, ry with respect to x, x sub s, ry with respect to y, ys, and this ys here is this ys out here. Then you hold ry constant, you differentiate y sub s with respect to s, and you get y differentiated with respect to s twice. Now group the terms as follows. rxx here, xs times this xs gives you x sub s squared. Grab the ryy, put it here, and you have y sub s squared. Then you're going to have rxy, ryx, and if you have enough continuity, of course, mixed partials are equal, and so we write 2 times rxy. You have an xs, ys, you have an xs, ys, so that's this term here, and then out here you have r differentiated once, but x differentiated twice, r differentiated once, and y differentiated twice. Okay, so to make the notation a little bit clearer, we're going to do the following. We're going to let over dot be differentiation with respect to s. And we're going to let differentiation with respect to t, the parameter that you actually have, that'll be a prime. So the curvature vector is the Frenet curvature times the principal normal, which is really the second derivative of r with respect to arc length. So that's r double dot. That's what we just computed up here. It's r double dot. And I've now written this last line here in terms of dots. So Rxx, x dot squared, Rxy, x dot y dot, Ryy, y dot squared, Rx, x double dot, Ry, y double dot. Now, the normal curvature is the curvature vector dotted with n, the surface normal. We've seen this formula here, but let's take the dot product of n with this r double dot here. N dot, these three terms, they will survive, but n dot rx, rx is a tangent vector, n is a normal vector. They're orthogonal. You get a 0. And the same thing with ry. It's a tangent vector. Dot n, 0. So you only have these three terms. Now let's examine these three terms. Rxx, Rxy, Ryy, dotted with n are these numbers. N dot Rxx, N dot Rxy, N dot Ryy. Second fundamental form numbers, E, F, G. Lowercase letters. So E, F, G. The x dot squared, how do you compute that? The x dt dt ds. And you square that. So x dot, the x dt dt ds. Y dot, dy dt dt ds. So you got a dt ds squared here. You're going to have a dt ds squared here. And similarly here, you're going to have dy dt dt ds. You're going to have dt ds squared. Pull out dt ds squared. Put it in the denominator as the SDT squared. If you look at what you've got in the numerator, that's nothing other than the second fundamental form, where the vector is x prime, y prime. You put the transpose here and you put the column vector here. Second fundamental form. And here in this line, I write this matrix as pi 2. Then down here, you want to look at that denominator, the SDT squared. It's the norm of the RDT. How do you do that? Well, here's the RDT. You've used the chain rule. dr dx dx dt, dr dy dy dt. And you dot it with itself. Well, you don't get just two terms. You have actually four terms, because this is really a binomial. You know, you use I and j, and you got I and j, and you got all mixed terms. You're going to have rx dot rx and an x prime squared. You're going to have down here ry dot ry and a y prime squared. But then you get the mixed term, this one and this one. Rx, Ry, Rx, Ry, x prime, y prime, x prime, y prime. And you have these two terms here. And if you recall back over here, Rx.Rx, Rx.Ry, Ry.Ry, those are the numbers that show up in the first fundamental form. Use capital letters there. So you have first fundamental form, x prime, y prime, x prime, y prime. Prime means you differentiate with respect to the parameter you have. That gives you the denominator of this expression that looked like black magic, but it's not black magic. Okay? Well, it behooves us to do an example. Let's check this out. Okay, we need a curve. So we'll use this family of curves that we got by taking straight lines in the plane and lifting them to the surface. We need tangent vectors. So we differentiate with respect to the parameter p, which is the parameter along each of those curves. Evaluate at p equals 0, so we're at the point 115 on the surface. Now we need to express this tangent vector in terms of the basis for the tangent plane. Now the base of the tangent plane are these two vectors, r sub x. The p means that we're evaluated at 115, r sub y. And the reason for that is that this is a three-component vector, and this matrix and this matrix they're 2 by 2s. You've got to be dealing with a two-component vector. And it took a while for me to realize this step. Crucial, essential, and it just got past me. And it wasn't until I woke up to this that things got better. Okay, so we make a linear combination of these two basis vectors, and we say, can this linear combination equal V? What are the A and B that do that? You calculate using solve, then you put that A and B back into here, and so you express this tangent vector in terms of the basis vectors. It's cos t sine t. Well, now you can form these bilinear forms. And linear algebra has this bilinear form command. Saves you a lot of work. This is the bilinear form you get with the second fundamental form. This is the one you get with the first fundamental form. And you take the ratio, do a little simplify, and you get an expression that looks familiar. You compare it to the Kn that we computed several ways earlier. Difference is 0. This stuff works. Continuing with this more modern look, we find the shape operator. Okay, how do we define or get our hands on the shape operator? U is a unit normal on the surface S. Chi is not a vector. It is the negative of the directional derivative of U in the direction of a particular tangent vector. So chi depends on U, and it depends on the direction in which you take this directional derivative. So you start with a tangent vector, and you end up with a different tangent vector. So you are mapping the tangent plane to the tangent plane. This map is called and you take your pick here, Weingarten or Weingarten. I think it's German. I think it would probably be Weingarten. Take your pick how you want to pronounce it. So it takes the tangent plane to the tangent plane. Okay, so t goes to this directional derivative, which is in the tangent plane. It has a matrix representation because it's a linear map. W is the name of the mapping, and it can be represented in this way, the product of these two matrices, the inverse of the matrix of the first fundamental form times the matrix of the second fundamental form, and this is what it looks like for this particular example that we've been working on. Now, a little aside here, I already pointed out the confusion that I had about dimensions. This map W is a 2 by 2 matrix, and when I computed vectors, they have 3 components. Very confusing. Go to the internet, look for some help. I got to this site. Same question. Okay, here's somebody asking the same question. All right, 3 by 3 matrix. Dimensions have 2 by 2. They don't match. And in none of these answers, I went through all of these answers, nobody ever says the problem is you've got to express the vector in the tangent plane with respect to the basis of the tangent plane. Okay? And until I figured out what to do, I was at sea. Well, now I'm going to try to construct the mapping W from first principles. So I'm going to use the directional diff command that's in student vector calculus. This vector calculus command says basis vectors will be, all vectors will be displayed as column vectors. But in order to use this directional diff command, everything that it applies to has to be a vector field. So I take these vectors and make them into vector fields. So Rx is a basis vector, rho x. Ry, rho y. Normal, I use nu. This is a general tangent vector using these basis vectors, and I will make use of that subsequently. Here's what the vectors look like. They look just the way they did before, except now they have the right structure for the directional diff command. Basis vector, normal vector, tangent vector. So here I'm taking the directional derivative of the normal in the direction of this basis vector and in the direction of this basis vector. Minus signs have been inserted. I call these little m1 and little m2, the little guys, little letters, three-component vectors. But I have to express those as two-component vectors in terms of the basis. So here is the general tangent vector. I want to express m1 in terms of general tangent vector. Same trick I used before. Big M1, big M2 are these two vectors, just like I lopped off the third component, but I now have a reason for lopping off the third component. Now I'm going to make the matrix that takes basis vector to M1 and basis vector to M2. Basic linear algebra says that matrix is going to have as its column these two vectors, because this times 1, 0 gives you back this, and this times 0, 1 gives you back that. So W turns out to be this matrix whose columns are these two directional derivatives, which were taken in basis direction. That these two vectors, the directional derivatives, are themselves in the tangent plane, I just verified by taking the dot product with the normal vector, and in each case I got 0, so mapped the tangent plane to the tangent plane. Let's look at the consequences of what we just discovered. Consequences are that the eigenvalues of W are the principal curvatures. If that's true, then half the trace is the mean curvature, the determinant is the Gauss curvature. And we can check that by computing the eigenvalues. If we float them, the numbers look familiar, these expressions look familiar. We had gotten mean curvature before, Gauss curvature before. Half the trace is this number, it matches. The determinant is this number, it matches. Now, just think about for a second why the eigenvalues of W should be the principal curvatures. Now, the principal curvatures are a max and a min. If you think about the Rayleigh quotient, bilinear form, you can get eigenvalues by max and min. So the connection between max and min giving you principal curvatures and eigenvalues of W, the connection's there. I'm happy with that. We're nearing the end of the journey. There are two more things to look at. One is called the Gauss map. And the Gauss map says take the unit surface normal and treat its components as if they were the parametric representation of a surface. So I did that. And this is what it looks like. I see some curves in that surface. I reproduced those curves using the space curve command. I said, what happens if you lift a circle to that surface? What would the curves look like? And this is what they would look like. The conclusion I drew was, I don't know what the Gauss map tells me. It didn't tell me anything more than I knew. I don't know why it's in the literature. Somebody can point something out to me, I'd be happy to know it. The final item I'm going to look at is this notion of geodesic curvature. But notice it says of a surface curve. This is not a curvature of the surface. It is a curvature of a surface curve. Here's the symbol we'll use for geodesic curvature, Kg. And it is the curvature of a curve C that lies in the surface. It's the Frenet curvature of its projection onto the tangent plane. There's an alternative definition. You get the Frenet curvature vector for that curve C. And you project it onto this unit vector, n cross t. N is the normal to the surface. T is tangent to the curve. And that vector zeta necessarily lies in the tangent plane. T is in the tangent plane and is perpendicular to that plane. So the cross product has to be perpendicular to both of those. So it's perpendicular to n. If it's perpendicular to n, it lies in the tangent plane. There's a formula for Kg. You're projecting. So you can calculate K dot zeta. And zeta is n cross t. Turns out you can express it this way. Second derivative of C with respect to t, that's like r double dot. And r double dot is k. But you differentiate it with respect to t, so you have to compensate to get the derivative with respect to arc length. Derivative with respect to arc length brings you the SDT in the denominator. There are 2 from here, and there's 1 from here. That's why it's cubed in the denominator. To implement the approach 1, this first definition, I'm going to need a projection. So I go to the family C that we saw earlier. By picking t equals 0, I get this curve. I need the tangent plane, so I use the tangent plane command from vector calculus. Here's a parametric representation of the tangent plane. I want to project this curve onto the tangent plane. Went back to basics. I just looked at the difference between them, and the norm squared is really the distance squared, but I just called it d. I want to minimize this distance, so I use calculus, derivative with respect to x and the derivative with respect to y, set them equal to 0. Solve for x and y. Then I place that x and y back into the tangent plane, so I'm getting a curve now in the tangent plane. There's the curve in the tangent plane. And to be sure that I've done that projection correctly, I drew this little picture here. This is the tangent plane. This is the curve I'm trying to project. The red curve is the result of that projection. It lies in the tangent plane, and if you look at it just right, you can see that they, in fact, line up one on top of the other. If you do it just right, there. Okay, so my projection is okay. I can now compute the curvature of this projected curve. I get this number, it simplifies to that, and until I can corroborate that somehow, it's just the number. I haven't learned anything until I can corroborate that by doing approach 2. We'll now compute this geodesic curvature using approach 2 formula. So I need the curvature vector at the point P, tangent vector at the point P, and the formula is k dot n cross t. These vectors turn out to be curvature, tangent, and this is the computed value of the geodesic curvature. It matches this number. So there's the corroboration we were looking for. And then finally, a picture. Tangent plane is the plane. Black curve lies in the surface. The red curve is the projection onto the tangent plane. Tangent vector, normal vector, black, green. Then there are these two vectors, this red one and this gold one. Now the gold one is zeta, because zeta lies in the tangent plane. The red one is the curvature vector, and the projection of this red vector onto this gold vector, that number is this geodesic curvature.